Hi, welcome you again to the stress lecture series. And in this lecture, I am going to discuss all about stress tensor and its components. So today's discussion about two things. Number one, stress tensor, and stress components and components. Okay, so before I start, and I think I would love to give you a basic idea of stress vector. So, what is stress vector? Yeah, stress vector. So, stress vector. Um, I'm pretty sure that you have idea about what is stress. Stress nothing but uh, force per unit area, right? So stress is defined something like that. Stress is defined force per unit area. So this is called stress. So what is stress vector? Because there is a force which is the vector quantity. That's why stress is also vector quantity, and we say it is stress. We say here stress is also vector quantity because of this stress, because it's a direction and the same time magnitude, right? So stress has also the stress direction and magnitude as well. So we call stress vector. But consider a plane. So if we consider a plane, say for example here, uh, say any arbitrary plane, say any three-dimensional object, say this or something like that, right? And we can consider any plane uh, or something like that, and if we apply any force here, say for example, if we apply any force here, say del f, and there is an area, say to that area I have applied any force, and the area is, say here it is del a, right? And the outer normal vector of the plane is n. That means normal. So any in arbitrary plane, say here it is arbitrary plane is normal vector, say here this means perpendicular to that plane is n, so is n. So if it is something like that, then we define the stress vector at any point, say here this any point p, at any point on the plane, or on plane, say this is the plane, right? This is the plane S, or at area del A, then uh, then the stress vector Tn would be, say Tn is limit, because we want the del A to be reduced to zero, and so del F divided by del A, right? So this is the stress vector condition, or stress vector, something like that, right? Yeah. So this stress vector, so this we know very well that for any perpendicular, something like that, any vectors has components. So for example, two-dimensional cases. So for two-dimensional cases, it is common. Say any arbitrary vector, say here it is any arbitrary stress vector t, then it has components here along this is tx. If it is tx something, if it is tx something like that, then it is t, right? Or the vector or something. Hello, walaikum salam. Hey, I'm sorry because I had a call to that. I'm sorry. So if this vector t, and say then its another component is tx, and along this vector is called ty, right? So if it is say for example, if we consider in plane or something, if any stress vector applied to any if any force applied to any plane, then it has two another components, normal components and shear components. So I'm going to make you understand what is the normal and shear components. It is the normal and shear components. So what is that? Say for example, we have a two-dimensional object here, a triangle. Say here this is the plane, right? And we have say RB sorry I'm going. Yeah. Say we have here plane, this is right, and we have applied force or applied stress tensor, say something like that, and it is a stress vector or traction vector something. So it's Tn, then its normal components would be perpendicular to the plane. So what is the perpendicular to the plane? Perpendicular to the plane. Sorry, it's the perpendicular to the plane. Yeah, I'm going to make then the perpendicular to the plane is normal component sigma, and shear component is parallel to this plane. So what is I'm going to change the color, it'll be better for you. Yeah, so it's a normal component of this traction vector or traction stress vector ds, and it's not a shear component is parallel to this plane, is say sigma s or tau s or something like that. In generally stress we express a normal component is sigma and a shear component as tau or something like that, but here for convenience we will use this sigma n and sigma s here. So we see, so if it is a three-dimensional case, say for example, if it's three-dimensional case, it's a two-dimensional case. So if we have three-dimensional objects like here, so let's draw a three-dimensional cube here. So it must have three components, right? Yes. In three-dimensional case, it three components. Say, I'm just going to change the color. Say yellow, yeah. So if it is x direction, say x direction, and this is the y direction, and this is another direction. Say this is y, this is x, and this is g. So consider a plane, say something like this, and I consider this plane, right? And if I apply any, say this is an arbitrary, so I'm going to change the color of it so it'll be better visualization for you. So say if I apply any force or any traction vector, say this t, say for example this is t, and it has normal component perpendicular to the plane, along perpendicular to the plane, so it is x to the x direction, right? X direction, say this direction. This normal component of t is this direction, say we consider this sigma x and x, right? And its other two components are parallel to this plane, this, so it has two parallel in this direction and this direction parallel to this plane, right? So y to the y direction and this is the z direction, right? So this component would be sigma x z, say for example, and sigma x y. So these two components are parallel to this plane, right? And these components are perpendicular to the plane. So any two, say if we write down this plane, right? So these two shear stresses, so these two are parallel to this, right? And this component is perpendicular to that. So if it is sigma x x and sigma, so it's three-dimensional, so I consider this three-dimensional or something like that, any object or something. Yep. So it's sigma x z and it's sigma x y, sigma x and y. So for three-dimensional cases, we found one component which is perpendicular to the plane and two components which are parallel to this plane. And so we know that the components parallel to any plane is called shear components. Shear component of stress of tensor, something like that, and perpendicular to the plane is the normal component. Alright, so we have already idea about this, how to write or notation of tensor components, right? So we have seen that this traction vectors or t, says this traction vector t n has two shear components and one normal component. So how we can write down this? So we have a relationship between traction components and tensor with a unit normal vector. The unit normal vector we have this stress vector has relation to normal component unit normal vector n in such like that t n equal to t n. So it is the unit normal vector and t is the components, right? So from the tensor lecture series, we have already known that if we write down components of a stress vector or something like that, then we can write down here t I equal to t ij equal to nj, right? So the how this is the way how we can write down this any components of an stress vector. So I is the uh, so okay. So before I going to start this, and I would make to what is the significance of x and x. There is two indices x and z. So what does this mean? Okay, this does mean x is plane from which the stress x, and this second index, this is the first index, and the second index indicates the direction to which the stress x direction. D-I-R-E-C-T-I. Say for example sigma xz, right? Sigma xz. The first is the plane, so is the x plane because from the x plane is normal to its xx. So from this plane, the stress component is z direction. So this is the z, right? This is the z. So it acts towards the z direction from the plane x. So that's why the first notation is the plane, and the second notation is the direction. So direction is the direction, and this is the plane, right? So from this is the components. So this is the stress vector. This is the stress vector is related to the stress tensor, or this is also called stress tensor because it describes all the components of the stress vector, and this is the outer normal vector of that plane, right? So we can write down so in three-dimensional case we have three planes, right? So I here, okay, I'm going to show ti equal to tau ij, and so I is a plane, right? I is a plane and j is a direction. dir is the direction. So we in three-dimensional cases we can get three plane, right? So in the above in the picture in the image we have seen there's in the three-dimensional case this is a plane 1 x plane, and this is the y plane because the outer we call this x plane because the outer normal vector outer normal vector of this plane is parallel to the x. The same way, if the outer normal vector of this plane is parallel to this y direction, it is called y plane, and the outer normal vector whose direction is parallel to the z direction, then it's called z plane. So we have x plane, y plane, and z plane, right? So we may have three we have three applied stress vector to if you want to describe any state of space of a cube, then we need to describe it for three-dimensional cases. Then we will have three planes, x plane, y plane, and z planes, and along these planes these stress vectors are so x plane. In x plane we'll call three components, right? In y plane we in y plane we'll get three components. One is normal, one normal, and two shear. Here is one normal and two shear, one normal and two shear, right? And same way in jet plane we'll get three components because three components, and one is normal, one normal, and two is shear because we have already seen that here on this plane, right? Yes. From this plane we have got one normal sigma xx and sigma xx and two shear xz and xy, right? So from the x plane we will get one normal is sigma xx, sigma xx, and other two because the first index must be x, so xy, and another two shear is xz, right? Same thing, we would get one normal yy, and the first index should be yx and yz. Same way we would get um, we would get for z plane one normal component is zz, and that is zx, and that is zy, right? So we have got uh, we have got 9 components from the 3 planes, from the 3 stress vector or 3 traction vector, right? Among which 3 are the normal components, and the rest of them, that means the 6 are the shear components, right? So we can write down this stress notation or stress vector component, something like that. So Ti equal to tau ij, it's a normal j, so we can write down. So if it's x, then we can write down here txx plus, sorry, txx times nx plus txy times nj, because the second index should be equal to the outer normal vector projection. Yeah. So you can write down t xz and nz. So these components are applied to the x direction only, right? Yeah. X, so not the plane x, but we can write down this component. So x y, so we can write here t y, say yx say it doesn't matter, yeah, yep. So t yx and so on, and this way you can write down tz or something like that, right? So you can write down this stress component. So this is called stress tensor tij. So from there we can write stress tensor, yeah. And these are the outer normal vector or something like that, right? So it's very easy to understand, and it's very simple, something. Yeah. Okay, so from this equation, so what you can infer or something like that. So if you write down or more detail, so you can say, oh sorry. So if we write down this fully in description, something like that. Yeah, I'm going to write it down. Yeah. So to describe this, so I can. Uh, so I can write down here T I 2 1. I think I made a mistake here because no, I didn't. I think no, I didn't make a mistake here. So I can write down this way or something like that, right? So we can write down here y, yx, yx, and x, right? So we can write down y, z, so this is yz, and z plus we can write down t, yy, and ny. So from there we can write down here. So t, z, x, and x plus t, z, y, and y plus t, z, z, and z, right? Yeah. So more interesting. So what are the interesting part, exact or something? Say, what does this component mean? Okay, so I'm going to change the color. Okay, so what does this component means? This component acts from the x plane and its direction is z, right? Same way, uh, um, what does this components mean? This means this stress or this components acts from the y plane and its direction towards the z. So this is the shear stress and this is the shear stress. The both shear stress acts towards the z plane, right? Acts towards the z plane. Yeah. In the same way, so I'm going to change the color so it'll be better for you to understand. Yellow, yeah. So this component and this component acts towards the y plane, right? Y plane. Thus the resulting shear stress, thus two shear stress acts towards the y plane, and this green marks shear stress acts towards the jet plane, right? So thus the resulting shear stress on the plane jet is what? On the plane jet, say for example tau z, resulting shear stress is T x z n z plus T y z T y z n z. So this is the resulting shear stress. This is the resulting shear stress acting on the plane jet. Similarly, you can write down resulting shear stress on acted towards plane j, plane y. So we can write down tau y equal to T x y n j plus T z y n y, right? And this it's very easy. What is the magnitude? Magnitude of the shearing stress. Magnitude shearing is resulting shearing stress on plane jet is nothing but, if you write down tau z resulting shear stress, we know it's very simple, right? Yeah. So T x. So what is that? X z. So I'm sorry, z. Yeah. X z whole square plus T y z whole square and whole root over, and similarly we can write down this magnitude of that, right? Yeah. Similarly, you can find out what are the mean shearing stress or the magnitude of shearing stress along the plane x or along the plane y or along the plane z. So something like that. Okay, for more convenient for computation, we can write down the traction stress vector or traction to the stress tensor to falling here as something like that. P equal to stress tensor times n outward normal vectors. So this is the stress tensor, right? Stress tensor, and this is stress vector or traction stress vector, or you can write it even traction, and this is the outward normal vector. Outward normal vector, something like that. Yeah. So that is clear. If the matrix T is known, from this equation, if the matrix T is known, the stress vector T on an inclined plane is uniquely determined, right? Uniquely determined from this equation, right? So in other words, we can say the state of stress at any point is completely characterized by stress tensor. Here is T, right? Yes. So we can write down this or something like that. So I hope you have enjoyed this discussion of stress tensor and its components, how we can use this, and what are the shear stresses and the normal components of that. So in the next lecture, I'm going to show you the symmetry of stress tensor. That means how the stress tensor can be a symmetric stress tensor, right? Yeah. Okay. Thank you very much for watching this video, and I hope I hope I'm gonna see you all on the next lecture. Thank you.